300 years ago. Okay, so this is a story of two bridges, and how does that factor into determining the radius of the Earth? So it all starts in a prosaic cubicle in a kind of a standard office building. And this is at Foster City, just a few feet from the edge of San Francisco Bay. So when you turn around right there at Foster City, and the San Mateo Bridge also is right there. So when you turn around after looking at this building, so that circle represents my window, a tiny cubicle, but an executive view for out the window. So this is a large panoramic window right there at my cubicle. My hierarchy in the corporation did not dictate this, but I told very few people about this lovely view.
Oh, would that be the Vista building?
What is it?
Is that the Vista building?
At that time, it was the Applied Biosystem building.
Okay.
Yeah, that was the company. So this is from the third floor. And just to give some orientation here, to the left, let's see, yeah. Oh, that doesn't show anything at all, does it? Huh, I'll be darned. Nothing at all. Okay. This is Mount Tam. This is downtown San Francisco. And this is Treasure Island. And barely seen here, all along here, is the Bay Bridge. This is between San Francisco and Oakland, the Bay Bridge. So this is the picture is taken from then down here, Foster City, in Foster City. So with this picture, then you get more curiosity. Well, can we see the bridge a little more clearly? And yes, you can. The company was very generous. They supplied a cruise for some of the staff, and it happened to be close to the Bay Bridge. So what you see on the right here, Treasure Island, and you can see these major piers. So this is a lovely trip that we got to see. So we got to see the bridge much more clearly, more closely.
What is that red circle? Is that something of interest?
What's that?
What is the red circle? Is that something?
The red circle is something that we will get into, and just focus on this. Notice that there's a large pier on the left and a smaller pier on the right. And there's the first pier to the west of Treasure Island, second, third. So with that, we can. So that's close up and in the real, but now let's use a telescope, an 8-inch Celestron telescope, and then take a picture from Foster City. All right, now this is 27 kilometers away. So now this picture is a picture of this bridge from here. So that's our 27 kilometers. You can see it's kind of fuzzy. But you can see the same piers that we saw before, meaning right here, you can see the large pier, and there happens to be a boat in front of it, and another ship out here, and an oddity inside this circle. And we'll figure out what that is. So now we've got
Richmond Bridge.
What's that?
That's Richmond Bridge.
You recognize the profile.
I've seen the wave many years. So
yes.
Lots of fun pictures. And just for reference, the piers on the Bay Bridge, they go Alpha, Bravo, Charlie, Delta, Echo.
Yes.
So if you refer to them.
Yeah, this is pier.
That's
C or D.
It's Charlie. Pier C.
That's pier C. Okay. Yes. So you can find this, on a topographical map. So here we know exactly where our line of sight goes. It goes from between these two piers and off to the north and slightly west. And here's a part of Treasure Island. So here's the Bay Bridge. And so we're viewing right through here where that circle was. Then taking another look. So here we are at the observer, taking a look at the Bay Bridge, and we're looking at the Richmond Bridge. And if you take this, let's see, here we go. We know where we are very closely, long last. We know where this is from the topographical map along there. 2 points determine a straight line. So we have no choice. We direct this line, continue north, and we find it intersects the Richmond Bridge. This meeting is being recorded. The Richmond Bridge, and it's very specific. It's the second tower from the west, Richmond Bridge. So it's because what's that? Click OK. Yeah. Let's see if I can. You know what? It is not showing my. It's not showing my cursor. About OK. Nope. It's all right. I have to get rid of that OK. I'm trying, but I'll have to exit the slide advancement and then go back into the slide advancement. This is a very convenient interface here. Let's see. All right, so we have no choice. It points to that particular arch or the tower of the Richmond Bridge, second from the west. And it's really kind of amazing how accurate that was. You know, it just really points straight to it. There's no ambiguity here. So 2 points determine a line. All right, so that's what we're looking at then. So this is the Richmond Bridge underneath the Bay Bridge. Now, what else can we do with this? This should spring to your mind right away. Oh, yes, and at the same distance is downtown San Francisco. So this is another photo of the downtown area. But we can do a lot. We can get the location, the longitude, latitudes of each of these two piers. We can find that the piers are slightly angled to the line of sight, 29 degrees. That is, this pier is closer than that one. And the angle is 29 degrees to the line of sight. So it's slightly foreshortened. This is the foreshortened distance, 335 meters. So we can use this as a ruler for everything else. So this is between pier C and pier D. So now we have the measuring stick. Now, you don't expect
just one slight error that maybe introduced, might have thought about this already. The elevation of the water is 67 meters. The tide level in the bay is about 7 feet, in 6 to 8 feet a day, basically. So it goes up and down.
right. So it's important to get the elevation, find from the engineering documents, the elevation above mean sea level. That's what this refers to.
Yeah. The lowest level is called MLL, leaving us saying the mean low level, basically.
Right.
And so anyway, because I was thinking in terms of when you do the final computation, maybe I'm getting ahead myself here. My apologies. When you do the final computations, you know, that number will factor into whatever there is.
Right. So you're talking about the daily tidal, twice tidal variation, 2 high tides, 2 low tides.
That's the number of water will change.
We're not dealing with tides. This is just from the mean sea level geoid.
Oh, I see.
So this is points down to the water at this moment, but maybe the tide the next day would be up at this top part of the arrow, and then maybe lower.
But it's a 67 meters part of my computation. I use in that computation.
Yes, this is the height of the bottom of the Bay Bridge to the mean sea level. Now, so we know that distance because we can use that as a scale. And then using this also as a ruler, we can measure this distance. And ultimately, what we're doing here is counting pixels, right? I mean, this is 1,300 pixels in the, close to 1,300 in the original picture. And this is 118 pixels. So that's really what we're doing, but still using this as a ruler. Okay, yeah, so now what do we do with that? We should imagine, of course, that how high this is depends upon the curvature of the earth. I have here a wonderful animation. It's down here observing in Foster City, and we're looking at the Richmond Bridge. And this twine is our line of sight. You can see that as the curvature gets greater on this animation here, that the line of sight gets lower in the compared to the bridge, the Bay Bridge. So what we can expect is if we could somehow increase the curvature of the earth, that would get lower in the field of view here. All right, so that's generally what we're going to do. We're going to measure that height. Not good is to measure the height above the water. That's very fuzzy. But what is sharp, or the sharper you're going to get in this picture, is the bottom of the bridge. So that's our line that we measure things from.
Then you mentioned counting pixels, 180 pixels. Did you actually count each of them?
Yeah, yeah, that's okay. So now it doesn't want to. You're kidding. There we go. So this is the relationship. Here we are, the observer, the line of sight, 6 kilometers from the observer. The line of sight gets closest to the surface of the water, about, I forgot, but about 6 kilometers out. And then it encounters the Bay Bridge and the Richmond Bridge. Well, here's the first point, the second point, and the third point. And from your analytic geometry, 3 points determine the circle. And in this case, the circle is the cross-section of the earth. Now, so what we need to do then is to get the mean sea level location as it is off of this line. We can use the line and then measure down to the mean sea level, measure down to the mean sea level, and measure down to the mean sea level here, 3 places. So that then we found 3 points that determines the circularity of that mean sea level. All right, so we're looking at a distance of 43 kilometers. 3 points, all right, the same thing. So this just gives you more detail about the 3.
இது ஒரு இது
Observers at
எர்த்தோட இது ரேடியஸ் எப்படி கண்டுபிடிக்கிறது கோல்டன் கேட் பிரிட்ஜ் வச்சு
Please mute yourself.
is the cross section of the earth. Now we're going to use 3 different models. We can't leave out the flat earth. I mean, what if that fits our measurements here? So, but we're going to use the 3 different models, kind of arbitrarily named, except for the first one, that's a famous name, triangle and refraction. Flat earth model, you can imagine what that is. 0 curvature, infinite radius. The triangle model assumes a spherical earth. That's all good. And the refraction model goes one more step. It assumes that line going through the air to the Richmond Bridge has a slight concavity downward. That's due to refraction, the varying index of refraction in the atmosphere. So the venerable flat earth model. So this one is, you use proportional triangles. It's a simple ratio problem. And you can find that the height of the Richmond Bridge, the top peak of that Richmond Bridge should be right at the bed of the Bay Bridge. So when we look at the flat earth, says that this peak should be right up here. Clearly, that's not so. So we say that, okay, maybe we can do better than that. Now, part of the problem with flat earth is with these models, you have to take a little different point of view. The flat earth model works very well for this room. You can draw an accurate diagram of this room, of this building, and have just as much precision as you can construct for any sort of construction. And so this model, the flat earth model, has its area of validity where it is sufficiently accurate for the purposes at hand. And that's really true for any model. So let's look at now another model. Round earth model, long in coming, but finally got there. This is a crowd pleaser. We get into some math here. It's a lot of triangles, and suffice to say, if you want to get into it later, we can, but given this height, given this straight line, given the height above the mean sea level here, and the 99-meter height of the tower, top of the tower of the Richmond Bridge, you can see that we now have our 3 points that will determine a circle. And we know this distance and that. All right, so what does that do for us then? Well, you can solve those triangles and then come out with a ratio of the sort of the accepted radius of the Earth. It's the USGS radius of the Earth, which is going to be, our goal is 1. Our goal is to get as close as we can to the USGS radius of the Earth. If you insert the measured value of X, that's the distance down from the bottom of the roadbed to the top of the Richmond Bridge. If you put that in there, you'll find that you get a radius 14% larger than the actual radius of the Earth. All right, so that's where we are with our accuracy with this round Earth model. Can we go another step? What other assumptions can we make? And let's don't discard the round Earth part of it, but let's see how we can modify it from there. So here's where we are right now. The flat Earth says that this peak, which you can barely see, but right here, should be up here. Not so good. Better is the triangle model, which places the peak right here. Better, much better. Now let's see if we can go still further, and let's add refraction to this model. And the problem with this model is not the assumption of roundness of the Earth, but this line is not straight. In air, because of the variable refraction of the Earth, of the air, it's slightly concave down. And we can model that. So round Earth. Now this is the actual calculation. This is the observer 13 meters above the surface of the Earth. And this distance this way is shortened 340 times. So it's all pulled in, right, from the distance. So that's in order to get the bridge Bay Bridge right here and Richmond Bridge tower, all on one graph. All right, so here's the circular, well, it's not circular anymore, but squash circle becomes an ellipse in this case. We're just compressing everything. But a straight line goes to a straight line when you switch this distance. This is not a straight line, it's concave down. So this includes the refraction. So it's got another little correction to it. And you can see that bending is going to strike a different distance below the roadbed of the Bay Bridge. All right, so let's, and doing the calculation, then you'll find you get this, and it's within 1% of the radius of the Earth. So now we're getting down to the pixel level. So it's kind of like, that's it. We've got 3 models and that successfully get better and better. And now we're down to just about all that our data could support. So this is the crowd pleaser that they have. So this is for refraction calculation. It's a partial differential equation. This is a derivative. H is the height above the sea level, and N is the refraction of air. And the refraction of air, all we care about for this refraction of the air is from 0 at the mean sea level to 99 meters, the top of the Richmond Tower. That's the only short section of air that we care about. So this holds for that short distance, for the refraction value. So plug that into this and do the differentials, and you come up with that curve that we just saw in the previous. All right, so
Question.
yeah.
But the amount of that, I mean, the underlying phenomenon that's causing that refraction has to do with temperature gradients above the water. That's what's causing the lensing or the bending. So there has, like, from a first principles perspective, you sort of figure out what that temperature differential is,
Yes.
and maybe iterate something. I mean, they're just sort of like if you knew nothing about the Earth, and you're just doing your measurements this way, you would sort of get a result and then see how close it might be. Somebody else's role.
What went into this was how do I go in reverse here? Yes, like that. So what went into this calculation is the ambient temperature that day and the standard pressure. I don't know what the air pressure was that day. I assume it wasn't that far from average. Then this goes into a formula found in a book called Astrophysical Quantities, and temperature and pressure enter into that calculation for refraction. So for the pressure over that 100 meters, just assuming that there was an exponential drop in pressure, but with a tiny drop in pressure over 100 meters. And the temperature is just making an assumption of the adiabatic lapse rate for that 100 meters. Could be wrong, I mean, the idea, it'd be interesting to rerun a bunch of different scenarios close to those temperatures, and just to see how much of a.
In aviation, pilots just use the rule of thumb of 2 degrees Celsius drop every 1,000 feet of elevation.
Right.
So, if you put that on a linear scale, then 99 meters is about 330 feet. So, about 0.6 or 0.7.
Right. Yeah.
But it's a very interesting equation.
Right. This is in full 3 dimensions, but all you need is 2, because we're just looking in the plane of this beam this, your line of sight. So.
Can I add a little bit to that, your answer? So refraction is caused by density, the change in density with altitude,
which is a function of temperature.
temperature can affect it, but even if it's a uniform temperature everywhere, it's still a change in density, just because there's more air at the bottom as you go up. So it's density decreasing, and the atmosphere is like a perfect gas, so yeah, there's temperature and pressure can couple in there. Maybe modifications to that, but it's primarily a density gradient, which is why these track like a refractive index, which is linear to density.
Yes.
Curious to ask.
Now, this is refractive index as a function of height. So the density is already factored in there, the elapsed rate is already factored in there.
Have you taken this different days with different temperatures, different weathers?
Here's the story behind this picture. Totally by accident, I left the company, and then a year later, I noticed there's a little Richmond Bridge in the picture. I didn't get a chance to go back and take another picture. Anybody want to do that project? Talk to whoever is sitting in that building these days. I think that'd be great fun, you know, to take pictures at different times, you know, and you could see this effect. If you could keep the geometry all the same, then you could see the effect of the changing temperatures, changing, you know, as we were just talking about, for the refraction. So you would actually expect to see that distant tower, Richmond Bridge Tower, to go slightly up, slightly down, depending upon the temperature that day. That would be fun, yes.
Still on friendly terms with this?
That's right. That's right. So let's see. So the refraction model does the best prediction. And for the value of X, that's starting with the USGS, US Geologic Survey radius for the Earth. It does the best job of matching our measured X. And it also does the inverse, so that you can expect then that refractive model would be the best to calculate the radius of the Earth. And flat Earth model is a clear loser there over that distance anyway. And here's another graph, radius of the Earth versus X. The measured value of X is 30 meters, and that gets you to 1% too large for the radius of the Earth. But you can experiment with some of the values.
So, you know, I think it's about 6,400 kilometers of the radius of the Earth. So you were within 64 kilometers of the actual or something. 6,400 kilometers for the radius of the Earth. So.
Oh, this is a ratio.
Correct. So you were within 1%, you said. So you were within 64 kilometers of the Earth.
Yes. Yeah.
Wow.
Yeah.
And that's very impressive.
Yeah. Right. Well, you think of what is the difference between the polar and the equatorial radius?
That's a technical, the Earth is an oblate sphere, and it's kind of squashed at the top. So, but I mean, I don't remember offhand, but they're pretty close.
Yeah. Yeah, there's other issues here too. And, you know, when you look at the image of this, when you look at the bridge, you know, remember that you can, there is refraction in this vertical direction, not in the horizontal, but in the vertical. So when you're doing this calculation, you have to look from the eye out to the Richmond Bridge. You have to look at tangent at that point. Because what you want to do, we're looking at this, all we're looking at is the angle with the telescope. That's all you can determine with the telescope, with an angle. So you count the pixels, that translates to an angle. But that angle is affected by refraction. There's more refraction here than here. So you have to run your calculation to the bottom of this Bay Bridge. That what I mean is the line of sight to the bottom of the Bay Bridge and the line of sight to the top of the Richmond Bridge, much further away. In both of those lines of sight, you take the tangents at the observer eye, because that's the direction. So you have to be a little careful, because what that allows for then is, you recall with the setting sun is normally brown, except you've seen the oblate spheroid, ellipsoid for the image of the sun that gets squashed as the sun sets. So you don't want that to happen to your vertical measurement. Let's see, I think that's. Oh, yes, conclusion. I gave this to the presentation of physics teachers, and underlying is models. Models are important. And the models have various components, you can put them together, and you test the validity of your model by comparing with observations. You include, here we see that including successive physical effects around Earth, refraction, improves the accuracy of the model. Oh yes, the Earth is round. But are we sure about that? I mean, after all, this is a post-conclusion. Well, it's essential in physics, but it takes work. And if you're a hard worker, that means you spend many hours at it. And you can get involved with what you're modeling, and you can be attached to your wonderful model. And you can try not to get attached, and that's a good goal. So the Earth appears to be round. So it's a little not as severe. That's all I've got. You have some questions? This is fun. Yeah, I've just got other.
If,
So you know.
yeah, if people have questions, raise your hand and we'll try and get to you as well. And from the audience, please, just go right ahead. I have one quote from a famous statistician, a British one. He said, all models are wrong, but some are useful. So, so this is very interesting work, and a lot of persistence in what you've done. Actually,
Many hours, yes.
figure it
So
out.
the thing is that the hours weren't committed all at once. First, you happen to notice that there's the Richmond Bridge there. And then you spend far too long trying to measure the height of that Richmond Bridge from the surface of the water. And you realize the surface of the water just not clear in that picture. So what is clear? Well, anyway, it's
Yeah, you were within 59 kilometers, which is the greatest.
oh right. Oh, this, yeah.
And for the record, Earthoscopy, it's questionable exactly what's the length of a stadia.
Right.
So it's either 1% or 10%. So
Okay, I've heard 5%.
5%, yeah,
But, you know,
1 or 5%.
something like
The
that.
length of the stadia is 440 yards.
It wasn't clear that they exactly.
But it might depend on.
There might have been 2 types of stadia.
Right.
Yeah.
So I've got copies of the paper that went into the teacher's journal. This is under the physics teacher. This was in October 2022. And then for those of you with stronger digestive powers, here's the one with the math. And
All right.
then here's a map.
It has all related the concept of the cosmic ladder.
Physics ladder?
That's one cosmic ladder. So, you kind of work your way, you figure out the distance from the earth to the moon, you figure out the distance from the sun. So have you thought about doing, further tandem? Yes. Have you kind of thought about doing?
Yeah. Yeah. That's an immensely complex story.
Yeah, but it's fascinating how you start with something small and work your way bigger.
Yeah. What I was trying to do was look at the cars on that bridge.
I've seen under both the bridges on eight times. So, I'll keep your calculations in mind. Some other concepts might come to mind.
Well, sometimes if you come up to the Richmond Bridge, I don't have a photograph of it.
I'd be happy to send you, I have a bunch of them. Yeah.
Okay, I would love to have one.
I'll say on the Bay Bridge and looking straight up.
Mhm.
I want to end the bridge on the Bay if you want.
Well, it'd be nice to get a picture that is somewhat like the photo here.
I can pull one.
So this is from south to north.
This is from South Mountains. And for what it's worth, that big tower, on the Richmond Bridge, that's the deep water channel. So the ships only go through that area. And on the Bay Bridge, the deep water channel is all the way over to the right. So, here, actually, that's right. Here, and here, is the deep water channel on the Bay Bridge.
Oh, I see, right, so the pier Echo, the E is
So
over
the
here,
here is the deep water.
and then there's Treasure Island.
Correct, yeah. So that's the ships will go through.
Oh, I see. So right through here would be the,
Where the ships come.
yeah. Huh. Yeah.
I think all sorts of variations, different days.
Different ways, exactly,
Yeah.
whether,
Weather, they just keep taking it.
But then keep the geometry the same, keep the telescope the same, keep
Yeah.
the view the same. Same.
composition of the air, it's a small detail.
Oh, yeah, it's 20 days. Forget it.
Yeah, I mean, there will be days when the Richmond Bridge disappears.
When it was built, I think it was the longest free span bridge in the world. It was 55.7 kilometers long. Back in the 50s. The bridge was around 550s. Yeah. It's a pretty long bridge. And then the record is last very long.
Yeah.
Yeah, early wording, later,
Yeah.
all kinds of stuff.
Yeah. And then, to me, interesting too, would be to change this geometry. And those are different points. A different tower, there's more than one tower of the bridge, of the Richmond Bridge, there's a tower. I don't know.
Yeah, in theory, you should do this from where you are. And hit the Richmond Bridge, basically.
Yeah, in theory, I mean, if you took 30 meters of wire, let's say, and with a flashing light on the end of it, you would see that right at the tip of that arrow. You would see that flashing light. And then I would imagine that like a green laser, you could probably see it maybe even at this distance. It wouldn't be a point because of the air. It would. And this is a tiny. This is a slight exposure. It's not. It would help to take a picture, even greater sensitivity, but a shorter exposure time. Right, because you get the wavering of the air. Because then everything would be a little sharper.
So what was the exposure time on this?
I don't have the record of that.
Okay, less than a second, right?
Less than a second, yeah, that's right, yeah. Yeah, the 8-inch telescope brought quite a bit of light in there. It was an Icon camera attached to the eyepiece.
Well, it's F10, right?
Well,
So you can sort of reverse engineer it. If you got an F10 system, optical system,
right,
what's the sensitivity of the,
yes.
for daylight.
But I probably let the shutter go and sense itself. Yeah, good point.
So I'm still on the refraction.
Yes.
So Wikipedia would say that with a 5 degree Celsius difference, the density of air changes by about 1.5%, something like that. So that's much more significant than the altitude change effect. So and the other phenomenon I observe is we're camping at Angel Island, and you can hear conversations in San Francisco as if it was spooky. The clarity just because of the lensing effect of the water. So I think that there's something operating here which has to do with that pretty significant temperature change over
What
was the number you quoted?
It's 2 degrees Celsius, where it's called lapse rate. It's 2 degrees Celsius every 1,000 feet of water.
And we're talking not
Now,
minuscule.
what's important in the curvature of the line of sight, though, is the height derivative. So if the entire refraction curve is shifted, then perhaps the derivative change is very little. Yeah.
So if you took the whole thing and moved it 100 feet above the
Right.
water, now we're talking pretty modest changes in temperature because you're. I mean, it's a very complicated problem. I think it's complicated because the differential in temperature that areas are covered is varying close to the water.
Yeah, the assumption here is just
It's
a
not
static lapse rate, so that's a linear change with height. But it is the derivative and not the absolute magnitude. If the refracted air was a constant refraction, whatever, then there'd be no effect, yeah.
If you had a higher road where you had a taller tower, you know, the calculations will.
Yeah.
That at the accuracy, the taller the
Yeah.
tower is.
Yeah.
Because, you know, you essentially be counting more pixels, so.
And I think what helps here, maybe even the most, is just the distance.
Yeah.
You know, you have,
Yeah, so
progressive increase of the effect of curvature.
yes, by the same token, the further away the tower is, that will also help in the accuracy.
Yeah.
Something close by will be super.
And those people in the audience, feel free, raise your hand, and we'll try and answer questions as well. Thank you.
Right, so if there was.
Yes, if you were to do your observation from Alvisa, for example, you know, you'd have get rather.
Get a longer.
Yeah, you get rather 30 or 40 count, well.
Yeah.
Yeah.
Was that? Find a tall building, yeah. Well, yeah, here, a fellow in Brisbane, when I was kind of casting about, took a video of the setting sun's shadow creeping up from the bottom of the building. So it's a distant object that, I guess the distant horizon was creeping up on this building, and from that he made a calculation of the radius of the earth. And so there is, like you were pointing out, the Lake Pontchartrain Lake, I think that's like 27 miles long, and the curvature is visible as you look at that bridge crossing that lake. And then finally, my favorite, the fellow in England that in the 1840s examined the level of water in a 6-mile long ditch. And he claimed that after careful measurement that the earth was flat. But, so I suspect that he made a mistake there.
A funny thing that, so, another guy and I taught, JLS middle school science, was math club. So we have this little after-school math club, and so we think of problems. You have middle school kids, and one of them was their house thing with the wells. And so we just kind of lay this out, let the kids try to grapple through this. And I put them on our family website. This is in '98. And this is before the Google algorithm. And so it basically looked for occurrences of a particular phase, like circumference of the earth or diameter of the moon. And for a solid 6 months, we were the #1 search result over NASA and over everything. This little goofy, problem set that was put on the internet for.
So it went viral, your calculation that you put up.
Well, for people, I hope nothing, nobody used it for, well, obviously, it had pictures of guinea pigs and everything else, so
Oh, I see.
but.
It's in your family website.
Just the family website,
Very
it was comical, but,
That's great.
NASA was like the third or fourth,
That's great.
And some of you guys might actually know how far can you see from if your height is 2 meters, and how far can you see before you hit the curvature?
It's not far, actually, maybe about
56 miles.
I'm saying,
Is that 56 miles?
you have to be pretty high to see that far.
Oh, from an airplane, I think that's how far you see.
Yeah.
I think it's more like, what is it, 10, 15 miles, it's a pretty small number, actually,
Well, everybody's got a different number.
to get the horizon.
Yeah, for this model, this is around 6 kilometers.
That's roughly,
Oh, in less than that.
it's very roughly, I mean,
Is that right?
don't look at me for I'll read it to Clinton.
Right.
But it's roughly the square root of 2 times the height times the radius of the earth. That's roughly as far as you get, about 5 kilometers, by my calculations, but don't take my word.
Well, if you're standing on the beach, the question is how close to the horizon.
Yeah, exactly.
Right.
5 kilometers out.
Yeah, that's not very far.
The Greeks were able to figure out the curvature of the earth because if you see, they weren't exactly standing at the beach, but if you see the ship's mast, we're dipping below the edge.
Yeah.
As they were sailing in.
Yeah, so if it is a flat earth, it's kind of a drop.
Yeah, so this flat earth thing,
Well, there should be-
there are still a few members.
So,
Sad to say, there's still some percentage of the
Yeah.
American population that believes.
I mean, you should not be all the way forward, that all that.
Yeah, clearly, it's only.
Well, we'll see if there's some complaints about this Zoom video. then.
All right. So with that, I just want to thank the speaker over time.
Yeah.
Thank you.